Hello, welcome everyone, welcome to Statistical Methods. In this video we'll be talking about the beta binomial model for estimating a proportion using Bayesian statistics. If you'd like to read this in the lecture notes, then head to the notes and read chapter 8. So Bayes statistics. So this is our first example of how to use Bayesian statistics. And we applied to the most simple problem possible. Applied to estimating a proportion. So if you remember, this was the famous coin tossing experiment. And we found that in the ML estimate, ML gave us the frequency. So the frequency was the ML estimate for the proportion. So you count the number of heads and the number of tails, and then you divide the number of heads divided by the total number of events, and then you get the frequency of the heads, and then this is actually the maximum likelihood estimate of the probability of a head. So as estimate of proportion. So that was the ML. So now we see how to do it in Bayes. Okay, so what we have here, we have our events. So let's describe our events. The events are 0 and 1. So let's say tails, heads. And then we have our PMF, probability mass function, which is, we have a probability that x is 1, that's P, and the probability that x is 0 is 1 minus P. So the mean of x is P, the variance of x is P, 1 minus P. So that's the PMF of this random variable. So that's Bernoulli. And the binomial would be similar, only that we have n repeats. So np, so x is then, can be anything between 0, 1 to n. So let's say the number of heads can be 0 heads or can be n heads or anything in between. The mean is n times p, and the variance is n times p, 1 minus p. And if we standardize this, so we'll look into xn, or for is then something between 0 and 1, and e of x over n is p, and the variance of x over n is p1 minus p divided by n. So that's the background. So that's also, of course, our likelihood when we compute the likelihood, so the binomial likelihood, and then we get p hat ml equals x over n. So that's our estimate of the frequency. So far so good. So now we want to apply Bayes' theorem. So for Bayes to use Bayes' theorem, we need a distribution for the parameter p. So to use Bayesian learning, we require a distribution to characterize our uncertainty about p, and what we are using is, so we need this both for the posterior and the prior. So for prior and posterior, and what we will be using here is the beta distribution. So the beta distribution has density, so has support, first of all it has support from 0 to 1, and our parameter p is of course from 0 to 1, so we need a random variable that has the support, and the density is a continuous random variable, and the density is fx, and it has two parameters, alpha and beta, and it looks like this. So it's 1 over b, and b here is the beta function, and then we have x to the power of alpha minus 1 and 1 minus x to the power of beta minus 1. So that's just the density. So let's look how does it look like. So we have some special cases. So how does this look? So alpha equals beta equals 1, then we get the uniform distribution between 0 and 1, so then it looks like this. It's just uniform between 0 and 1. So this would be beta 1, 1. It can look like this when alpha and beta are larger than 1, so it has a hill shape. It can look like this when alpha and beta are smaller ones, so that's U shape, and it can also look like this. It can be slope shape when, let's say, alpha is larger one and beta is smaller one. That's slope shape. So you can see it takes all kinds of forms, and it's always between 0 and 1. And the mean is given by, so the expectation of p is alpha divided by alpha plus beta, and you can also write down the variance of P, that's, let's call this is mu, so then the variance of mu is mu 1 minus mu divided by alpha plus beta plus 1. So that's how the beta distribution looks like, and what we will be using the beta as a prior, and then we go from prior to posterior. So beta prior distribution, and we write this as follows. We write P is distributed as beta with parameter alpha and beta. So alpha and beta are given, so we need to specify alpha and beta, and we could just use 1 1 if you want uniform, but we can just use any we want. Then of course we have a prior mean and prior variance, so we have prior mean and prior variance, and of course we can use the prior mean and prior variance. So prior mean is, of course, call this mu prior, and also sigma squared prior, and the mu prior is a function, is of course alpha divided by alpha plus beta. So it's a function of alpha and beta, and the same with the sigma prior, because it has the same function as above. So, and this kind of allows us to choose alpha and beta. So if we know roughly where we expect it to be, what the variance is, then we can get an idea what alpha and beta we should specify. So now we compute the posterior distribution. Compute posterior distribution, and the posterior distribution we compute using Bayes' theorem. So for this we need to have a likelihood, and the likelihood is, of course, that x given a parameter p follows the binomial distribution with n and p, so n is our data, and p is the total number of experiments, and p is the probability. So we have fx given p is just the usual binomial distribution, so just the same we used before when we actually used maximum likelihood. And then applying Bayes' theorem yields, so it yields, after some calculation, it yields for the probability distribution of p given x. It turns out that this is also a beta distribution, but now with different parameters, namely alpha plus x and beta plus n minus x. So we prove this in the worksheet 5. So, or you prove this. Proof is in worksheet 5. So you can work this out. So, but the key thing is the prior and posterior are both beta, so from the same family. The posterior mean which we can view as a point estimate is the expectation of this x given p, and that turns out to be x plus alpha divided by n plus alpha plus beta. So that's the posterior mean, and compare this to p hat ml, which is x over n. So you can see it's kind of a similar thing, only that alpha and beta play the role of actually observations. So alpha, beta play the role of observations. So if we would use maximum likelihood, so in this case the difference between base and maximum likelihood is simply that the prior adds information, and that's what prior is actually doing. So prior acts like additional data, and this is why we're actually using Bayes learning in small sample regime, because when we don't have enough data, we basically have to sort of invent data, and this invention of the data is mediated by the prior. So you can see there's no surprises here other than that. So we can also write down the posterior variance. And the posterior variance is the variance of x given p, and that turns out to be the mu posterior times 1 minus mu posterior divided by n plus alpha plus beta plus 1. So, and compared to the posterior variance of the ML, you see also that we have again alpha and beta plays the role of observations. And most notably, so if alpha beta go to 0, then we get back maximum likelihood. So the ML estimate is contained in the Bayes estimate. In the Bayes estimate. So in other words, ML is a special case of Bayes. In this example, but you will see this is actually generally true of Bayes. So the Bayesian way of learning is generalizing likelihood learning, and as we will see, it's also applicable to areas, problems like high dimensional problems where standard maximum likelihood is not applicable. That's it for today. So you've seen now you can actually apply it to standard cases, and in the next few videos we'll discuss other examples as well. So until then, have a good week and see you in the next video. Bye bye.